Alrighty, folks, welcome to History of the Atom Notes, Part 3. I almost put up a 2. Part 3. Gonna be a good time. Now, we left off last time with the gold foil experiment done by Ernest Rutherford. So if you remember, we learned quite a bit from that experiment. So he was firing those positively charged alpha particles through some gold foil. So this right here is our foil, this section. Here comes an alpha particle. Most of the time they go straight on through. So this guy goes straight on through. This guy goes straight on through. And sometimes they would deflect. So it's like, bing, go like that. And so what he learned was like, okay, number one, atoms are mostly empty space because most of these guys are just going straight on through. So again, most of them are just going straight on through. But he also learned that there is a nucleus. There's some sort of dense center that must be positively charged and really small. And that was what he called a nucleus. And he realized because every time something bounces off, those positive alpha particles bounce off something, well, it can't be all empty space. There must be some sort of dense, positively charged center in there. And so the idea of the nucleus is born. And so that brings us to our next guy in the history of the atom, Niels Bohr. Call him Boring Bohr because he just sort of looks like Eeyore from Winnie the Pooh. At least I think he does anyways. So here's his model of the atom. So we got the positively charged nucleus right here in the center. And he sort of pictured electrons just sort of are around it, kind of orbiting it like this. So like these electrons are just sort of like, woo, woo, just kind of going around like that with the nucleus at the center. And so what we say is that electrons orbit around the nucleus just like the planets orbit around the sun. Okay? So that was his idea here. And each orbit is a different energy level. So these electrons are orbiting here. They're orbiting the nucleus. And every time you're in a different ring, so this electron right here is in this first ring. And that's a different energy level than this electron right here, which is in the second ring. And we see that what he sort of thought was that the further from the nucleus an electron was, the greater the energy. So these electrons here, like this electron and this electron, were the lowest energy electrons. And then this electron right here and this one were higher energy. And if you had a guy out here in this third ring, this would be the highest energy electron as it's orbiting in this third ring right here because it's farthest from the nucleus. So the farther you get from the nucleus, the higher energy the electron must have. Now, one kind of problem with this, so Bohr's model said electrons are in specific places and that we can predict where the orbits are at all times. So he was kind of like, okay, we should be able to predict exactly where an electron is at all times. So if it's on this perfect little path where it's like, perfect little circle, not going anywhere, not doing anything crazy. So he's like, okay, so in 1 second, the electron should be here. And another second, the electron should be here. The next second after that, it should be here. So he was like, okay, electrons behave perfectly. They do exactly what we expect them to do, which we're going to find out here soon that that's not the case. And that was the biggest problem. So Bohr's model was helpful, but it was a little too clean, if you will. So the idea that electrons orbit the nucleus perfectly, just like the planets orbit the sun, it's a nice idea. It's kind of coming full circle. Pun intended. You guys see that? Because it's like, all right, the smallest atoms do the orbiting, the planets and the sun do the orbiting. But it's a nice, clean explanation, but it's not exactly how things work. Now, enter James Chadwick. Okay, so here's James Chadwick. He's credited with discovering the neutron. Basically, he had a big chunk. I think it was a beryllium, maybe. Can't remember off the top of my head. And he would blast it, and little pieces would fly off of it. And he would look at these little pieces, and they had the same mass of a proton, but they didn't have any charge. So we had these little chunks that were the same mass of a proton, but no charge. And so we called them neutrons because they're a neutral charge. Now, here's some interesting fun facts about James Chadwick. And you know what a nickname is for James? Is Jimmy. So his buddies call him Jimmy. And you start looking at this guy, you're like, man, he has a long face. He's got like a really long face. You ever notice that? Like, look how long this man's face is. And you start kind of visualizing, you know, Can you do something like this? Bum, bum, bum. Jimmy discovered the neutron. You guys hear where this is going? This is Jimmy Neutron. James Chadwick is Jimmy Neutron. I never knew this till like last year, okay? Like Jimmy Neutron got his name because James, aka Jimmy Chadwick, discovered a neutron. Jimmy Neutron. Look at him. Long face. Long face. He doesn't quite have the same haircut. But I mean, come on. You know Jimmy Neutron's made after this man. Like his face, what is that, like half a mile long? That's crazy. It's like long like my face. Is this crazy? Jimmy Neutron? James Chadwick? Crazy. I know you guys are laughing. I know you guys are laughing at home. All right, my jokes are still good. Don't worry, Mr. P. All right, so that's James Chadwick. Now, we got to talk about how atoms emit light. Okay, so now that we're familiar with Bohr's model, we can kind of get into this sort of thing. So some terms that you need to understand. Ground state versus excited state electrons. So ground state electrons are really low in energy, okay? So again, low energy is close to the nucleus. High energy is far from the nucleus. So like this electron right here would be like in its ground state because it's very close to the nucleus, okay? Now excited state is an electron that's high in energy. So if we were to make this electron go from a ground state to excited state, that means it would have to jump at least one ring up. So maybe it jumps here, or maybe this electron jumps all the way up here. So this right here is an excited electron, okay? Because it's not in its ground state. Now, some things to clarify. Let's say we had a couple of electrons here, and we had another one right here, okay? So if this electron right here, if this jumps up to this ring, that's excited. But this electron, if it's starting in this ring, it's ground state. So just being in the second ring doesn't mean something is ground state or excited state. You have to think about where the electron started. So this electron, since it's starting in this ring, is in its ground state, whereas this electron, if it jumps this ring, it's in an excited state because it is a ring higher than it normally hangs out in. Now, if I want to get this electron excited, I have to have it jump here or even jump up here. So that's the idea of ground state versus excited state electrons. So here's how light is emitted. Electrons start, so there's 5 steps to light being emitted, and you need to know all 5 of them, okay? 5 steps. Step 1, electrons start at the ground state, where they're close to the nucleus, and they are low in energy, okay? So step 1, you have an electron, it's in its ground state, closest to the nucleus that it can get. Step 2, the electron gains energy, and it jumps to a higher energy orbit, okay? So we're going to focus on this electron right here. So this electron started at the ground state, is as close to the nucleus as it could get, and we're going to add energy to it, okay? And it's going to jump to a higher orbit. So we put energy into the electron, and then it jumps to a higher orbit, okay? So it's not like it jumps to a higher orbit, then it's higher energies. We put energy into it, and that causes it to jump to a higher orbit. Step 3, the electron then falls back down to its original orbit in a photon of light. And it releases a photon of light, sort of like a ping pong ball falling down the stairs. Okay, so what goes up must come down. So we put a bunch of energy into this electron. It got excited, but it's only temporary. And so as it falls back down, kind of think of a ping pong ball and some stairs, doink, doink, doink. As it falls back down, it releases a photon of light. So as this falls back down, what will happen is a photon of light flies off. Okay, photon. And then if this were to fall down again, doink, doink, okay, those would both have photons firing off, okay? So photon is basically a small little packet of energy in the form of light. It's a small little packet of energy in the form of light. And so photons are light, that's what they are, and the different amounts of energy are different colors. So for example, if the electron fell from here straight down to here, that would give off a lot of energy, and that'd be one color of light. If it fell from here just to this one ring below, it would give off a smaller amount of energy, and that'd be a different color of light. So different colors of light are due to the different energies of the photons giving off that light. And so Bohr's model could predict these colors, but it only worked well for hydrogen. And that's because hydrogen is so simple. So Bohr's model was good at predicting the colors of light that would be given off when you excite the electrons in an atom. And it works best for hydrogen. It works okay for helium, kind of all right for lithium. And it gets worse as the atoms go down the periodic table. So it works best for hydrogen, which is the simplest atom, or the simplest element, I should say. It only has one proton. So this model is good, but it's not great because it only works for the small stuff. So again, you need to know all these steps of how light is given off. All those steps for how light's given off. And let's talk briefly about light energy. Okay. So the lowest energy are your reds. Okay. So your reds are the lowest energy light, and the highest energy are violet. So the highest energy is violet. So a photon that fell a small step, so it just fell like one ring, okay, that would be giving off maybe some red light. But a photon that falls from like the fourth ring all the way down to the first ring, that could be giving off some violet light, okay, because that's going to be a higher energy drop off. Okay, now up next, Dr. Yates, Miss Bay, and I have a video where we show these different colors of light that represent the smaller or greater jumps, or I should say falls, of the electrons from excited states back down to their ground states. So check out this sweet video that we totally made for you guys to help explain these a little bit more. All right, so the first sample we're going to test here today is a tube of hydrogen gas. Okay, so remember, this is the element that Bohr's model predicted the best. Okay, so what I'm going to do is I'm going to flip this switch on. It's going to send a bunch of electrical energy into this gas. And what's going to happen is those electrons in there, they're going to become excited temporarily. They're going to jump up. They're going to fall back down. As they fall back down, they're going to release light. So with the glasses off, all those combinations of falls by electrons look like this. And then when we put those glasses on, we can see the different individual falls of electrons. So you see a nice little barcode emission spectrum. Now, you may see a little bit of red in that barcode. Now, red is the lowest level energy, so that means that's an electron that's fallen not that far. So maybe it went from the second ring down to the Miss Bay's having problems. Sorry. So maybe it's falling from the second ring down to the first ring. So that's going to be a pretty small fall. Not that much energy is being given off by that photon, hence the red light. But you may also see some blues and some violets. Those are going to be an electron that went pretty far out, maybe like the fourth ring, and it's going to have a pretty big fall back down to its ground state. So its excited state, maybe many rings up. Its ground state is going to have a big drop off, and so you're going to see some pretty high energy, those violets and those blues.
All right, so the next sample we're going to do is helium. This has 2 protons and 2 electrons, so we're going to have a different color and a different barcode than we did with the hydrogen. So again, we'll start first. This is the color with it without the glasses. And then when you put the glasses on, you should be seeing a different barcode than you did before. So what you're seeing here now is you're seeing the similar red color down here at the bottom. There's a nice another yellow line in here, and there's a few more because there are more electrons jumping and falling. Again, when they gain energy, they jump far away from the nucleus, and then they fall back down, and as they fall back down, you see this different line spectrum. Perfect. So this should look different than the one you just saw in hydrogen.
All right, for our final one, well, the next one we're going to show you here is going to be neon. Now, neon has more electrons, 10 protons. Those 10 protons pull harder. They're going to pull those energy layers closer to our nucleus. And here's what a neon's going to look like without the glasses. And if we add the glasses in, you should see a lot more color bars in here. A lot more color bars, again, because we have more energy levels getting compressed into a space that we can see them. All right. And just kind of like what we were doing before, if we look here up on our screen, we have, again, a lot more energy bars here, right? So our electron, it can hop down. Right? It doesn't have to go as far. The energy levels are compressed. And we can still see the blue. Now, what you should see is about the same height in here, right? This is red. Here's our yellow. That's just telling you the energy of it. So that's why we see the lines lining up here. It's just that these are now all pulled closer, really close if I do it that way, and things get pulled in.
Here's Mercury with the glasses off. Here's Mercury with the glasses on. Love that purple and blue color. Oh yeah. Looks real nice.
Probably should see a different barcode even more on this one.
Oh yeah. Different barcodes for every element.
So now the next sample that we're going to do is what is mostly the most of the air is comprised of. That is nitrogen. So here is nitrogen with the lights or the glasses off. Here's nitrogen with the glasses on.
What a beautiful spectrum. My goodness.
It's a good spectrum.
Great spectrum. That's one thing we all know about nitrogen. It's a great spectrum.
All right.
Okay. I hope you guys enjoyed those demo videos. Now, to really just send things home, let's go over this one more time, exactly where light comes from. Step 1, electrons are in their ground state, so they're going to be in some sort of lower orbital, like this one right here. We gain energy somehow in the electrons, so maybe that's you're flipping a switch and sending electrical energy into those electrons. It's probably something like that. You could put them over a flame, potentially, but somehow this electron gains energy. And when it gains energy, that causes it to jump to a higher ring called the excited state. It's in an excited state now. What goes up must come down, though. And so because this electron can't stay up there forever, it will fall back down. And that extra energy that made it excited in the first place will be released as photons of light. So a small fall like this might release some red. A big fall like this might release some violet. Red being the lowest energy photons, violet being the highest energy photons. That's History Atom Notes part number 3. That's how light is produced. Yeah!